Welcome everyone to our second lecture. Last time we gave a teaser of the course, and now we're going to start talking about matrix representations with more details. Remember, for us, G is a group and often is going to be the symmetric group. And the elements of pi of Sn are denoted by permutations. So we have a permutation here in the group. Okay, so first we're going to talk about matrix representations. Okay, so let's remember the definition. So a matrix representation of the group G is a group homomorphism X from the group to the set of D by D invertible matrices. So I guess this is a matrix representation of degree D. So what does it mean to be a group homomorphism? So this means this is equivalent to the following. It means that this map sends the identity element of the group to the D by D identity matrix, and if I have the product of two elements of the group, the associated matrix is the product of the respective matrices of G and H. Okay, so this is equivalent. So I think we started to see some examples of this. So when D equals 1, if I send any element of the group to the number 1, so the 1 by 1 matrix that is 1, this is the trivial representation. And so when D equals 1 and say the group is a symmetric group, if we take a permutation and we associate to it its sign, so 1 if the permutation is even and minus 1 if it's odd, this is the sign. This is also a representation, and this is called the sign representation. Okay, so let's see another example of a degree 1 representation, but now our group is going to be the cyclic group on n elements. So this is the group with the identity, and I have a generator so that G to the n is the identity. Okay, so I have n elements. So I want to find all degree 1 representations. Okay. Oh, okay. So say that X is such a representation. So if Z is the image of the generator, then what should be true? Well, so let me go back to the definition, and I'm going to call these two properties 1 and 2. Okay. So let's see. So Z to the n would be the image of the generator raised to the n. Okay, so this is G. But by the first property, this is the same as, by the second property, this is the same as the image of G to the n, X of G to the n. And this is the identity. And X of the identity by 1 is it's the identity 1 by 1 matrix, which is just 1. So if Z is the image of the generator, then Z to the n is equal 1. So i.e. Z is an nth root of unity. Okay, so that restricts what the values can be. So for example, for n equals 4, there's 4 possibilities, so there's 4 representations, because once I know what happens to the generator, I know what happens to the other elements of the cyclic group. So if n equals 4, I have 4 such representations. And they're characterized where they send the generator, so I send it to 1, or I send it to I, or I send it to -1 or -I. Okay? So there are 4 degree 1 representations of the cyclic group. Okay? Any questions? Okay, good. So that's for degree 1, and we saw also an example of degree n. So if we want the degree to be n and say the group, I guess this should go kind of backwards, but if the group is a symmetric group on n elements, then we saw an example of a representation. So we can associate to a permutation, we can associate an n by n matrix, which is the permutation matrix. So if we send the permutation pi to the matrix the n by n matrix xij, such that xij is 1 whenever the permutation sends j to I and 0 otherwise. Okay, so I just get the permutation matrix. This is called the defining representation. Okay, so that's kind of a few examples of matrix representations. Now, so we're associating to each element a matrix, but this somehow is dependent on, well, you know, if you remember, matrices are examples of linear transformations, but a linear transformation of a vector space can have of a finite dimensional vector space can have different matrix representations depending on the choice of the basis. So we're going to now have a more abstract definition of a representation where we don't necessarily have a choice of basis. Okay, so this is going to be a little more abstract, but it's going to help us in what follows. So this is this is the language of G modules. Okay, so we will relate both. Just let's hang. So let's hang in for a second. Okay, so so for us now, V is going to be a vector space over C. Okay, and now GLV is the set of all invertible linear transformations. From V to V. So all the invertible linear maps from V to V. Okay. So now here's the definition. So our second definition. So we say that V is a G module if there is a group homomorphism rho from the group to this set of invertible linear transformations to GLV. So this is what's called the general linear group of V. So what is this kind of maybe is a bit of a scary word, group homomorphism. So what does that mean? So this is equivalent to saying the following. Oh, sorry. Just let me make some useful shorthand. So this map rho to each element of the group associates a matrix that can then act on V. So if I have an element G and I get the associated transformation and I act on V, I'm going to have a shorthand for this, and I'm going to call this GV. So I'm going to say that the group acts on the vector space by G acting on V is what you get if you obtain the associated linear transformation, rho G, and you apply it to V. Okay? So I'm going to use this shorthand. Okay? So being a group homomorphism is equivalent to the following conditions. Well, I need that in this shorthand, when G acts on V, I obtain something else in V, in the vector space. So this is capital V. I also need that it respects the structure of the vector space. So if G acts on the linear combination Cu plus dV, well, that's the same as CGU plus DGV. Okay? Yeah, so these are vectors here. Okay? And I have a third condition that says that I respect the structure of the group. So if I take the product of two elements GH in the group and I apply that to the vector V, that's the same if I first apply H to V and then apply G to that. Okay? And lastly, the identity of the group acting on V, on a vector V, leaves the vector unchanged. Okay? So saying that I have such a group homomorphism is equivalent to saying that I have these four conditions. Okay? Okay, so it's a more abstract definition. So let's keep it up here. Nope, I meant. Sorry. So let's keep. Oh no. Okay, almost there. So let me get rid of this. Let me move this up here. Yeah, get rid of this too. And this. Okay, so let me put this here. So we have this definition here. So let's make some remarks. So if X is a matrix representation of G, we can it is G module by letting, so we define the action of the group on V to be exactly what you would get if you get the associated matrix X of G and you apply it to V. Okay, so in that way, matrix representations are themselves G modules, and conversely, if we have a G module and the dimension of V is D, then if we pick a basis, of my vector space, then X of G is then X of G would be the matrix corresponding to the representation rho G. So in that case, we let X of G be the matrix corresponding to rho G with respect to the basis B. Okay, so we can go back and forth from a matrix representation and a G module, so that we at least we're not, we're thinking making things more abstract, but we're not, but we can go back and forth, so we're not losing generality. Okay, so let's see a benefit of this, of working with G modules, and so let's see such a benefit. So let me get rid of this. Okay, and one such benefit is that you might remember group actions from group theory. So let's recall what that is. So say that S is a finite set. Say that I have n elements. We say that G acts on S if we have an action. If we have an action of G on S satisfying the first property we see here, the third, and the fourth property. So that's what it means to have a group action on a group acting on a finite set. So we're just missing two. So it's kind of very close to the definition of a module. So so let's see what we can do to make to have two being true. Okay. So so to make this this a G module, we need to create a vector space. So we're going and this vector space should the elements of S should be themselves bases. So let me have some notation for this. So I'm going to call C S, and I'm going to capital S, kind of it's kind of bold. So this is the span of, so be viewing the elements of the set as vectors themselves. Okay, so if I do this, I can then consider linear combinations of the objects of S. Okay, and so we define this vector space, and we let yes. So now if a vector in this space would be something like C1 S1 vector plus Cn Sn vector, and then we define the action of the group component-wise. So we let G of so one of these vectors, we let it be so if G acts on this vector, it means that we just so it just acts component-wise. Okay, so it will be C1 G S1 plus C2 G S2 Cn G Sn. So and now each of these, so this would be just so GS1, where S1 is the vector corresponding to the element S1, would be the vector corresponding to whatever element you send this. So if G sends S1 to Sk, then this would be the vector Sk. Okay. So this would be whatever Si each of these corresponds to. Okay. So I define it this way. This is the definition, and that way, 2 now holds. So this we make it hold. So then this becomes a G module. So from a group action, we can obtain a module. Okay, we can obtain a representation. Okay, so let's see. Let's look at a concrete example of this. So I think now we have the definition of the module. So let's go here. So so the punchline here is that this vector space is a G module. Okay. So from any group action, we can obtain a G module. So let's look at an example. So this would be example, I think, 5. So if G is the symmetric group, it naturally acts on the set 1 up to n. Okay. So now, so so this group acts naturally here. Okay. Sorry for the handwriting here. Okay. So now, if we let CS be just the span, and now I'm going to write these numbers bold, so they mean vectors. Okay. So think of the vector corresponding. The vector corresponding to the number I to be just kind of the ith elementary vector in some sense. So so this is a this would be an SN module. Okay, and then so what would be the action? So if I have a linear combination of these elements, then the permutation would act by just permuting this element. So C1 and whatever. So if 1 gets sent to pi 1, then I can consider the vector associated to pi 1 dot 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 Cn pi n. Okay, so that would be the action. So for example, so say that n equals 2. Okay, so if I have the permutation, so for example, if I have if pi is the permutation that 1 gets sent to 2, okay, so then pi of A1 plus B2 would just be A2 plus B1, okay, and if we want to so remember that a G module, we can turn it into a matrix representation by choosing a basis. So if we let B be just the standard basis, so 1, 2, then you can check that the matrix associated to the permutation, the transposition 1, 2, would just be, well, where do I send 1? I send 1 to 2, and I send 2 to 1. Okay, and this coincides with the permutation representation. So you'll prove that in the homework. With the permutation representation. So sorry, it coincides with the defining representation. Okay. Yes. So I forgot to mention one thing. So we saw that from a group action we can obtain a G module. So this G module has a name. So it's an example of a permutation representation. So it's called the permutation representation of S. Okay. Of G, sorry. Okay, because it's just permuting the elements of the basis. The action of G is just permuting the elements of the basis. It's not sending the vector S1 to a linear combination of the S's. It's sending it to another S. Okay. Good. So yeah, so in the homework you'll show that for the symmetric group, this permutation representation coincides with the defining representation. Okay. Okay. So let's look at other examples of representations. So let's do one more, a very important one. So again, it's coming from a group action. This is called the left regular representation. Okay, so a group acts on itself, right? Because so remember that from group theory. So G acts on itself by right or left multiplication. Let's choose left multiplication. right? So so you know the G acts on H by just being GH. Okay, so so it acts on itself. So and this is a group action, so we can obtain a representation from this. So so to turn it into a module, we need to define a vector space where now the elements of G are a basis. So we're going to give this a name. We do the following. So we're going to define C of G. So this is going to be the set of all linear combinations of the elements of the group. So maybe I should say that the group is finite, and I have this n elements. So now I can so this notation here, CG, which is called the group algebra of G, is just a set of linear combinations of the elements of the group. Okay. So this is the group algebra, and why do we call it an algebra? Because, well, the multiplication of these elements is well defined. So if you have, we can definitely, like, yeah, we know how to multiply this. So if you have an element, of this group algebra, C1 G1 plus Cn Gn, and you have another element dg1 plus dngn, we know how to multiply this. So this would be the summation of I and j, ci dj, and I guess we have to figure out what element of the group we obtain when we multiply gi by gj. Okay. So this is so that's why it's called an algebra. We also have multiplication. Okay. So so this is a so we call this representation the one associated to the group action of the group on itself by left multiplication. We call it so we call this the left regular representation. Okay. Okay, so here in this kind of, I was just illustrating that there's an algebra that you can multiply, but here, this is how you turn it into a vector space, and this is a G module. Okay, the group algebra is a G module. Okay, and this is called the left regular representation. Okay, so next time we'll talk about another example of representation that you can obtain from cosets. So we'll recall that from group theory, and then we will talk about reducibility and Maschke's theorem.